will tell us about how to do AMO physics without the A.
Yes, so unfortunately I will actually not quite do that. So looking at the program, I in the end decided to change the topic a little bit. So now Hussein has actually already advertised it yesterday in our panel discussion, so I feel kind of a little bit pressured or obliged to say something. And yes, so the idea was to, as Kaden just said, right, to drop the A and focus on the O. Yeah. I'm too loud. Okay. But I still need it. Yes. Sorry, I don't. But it keeps you awake, right? Is it better or further away? Or? Yeah.
There might be a volume button.
I think you cannot put it away
Okay,
because of the recording.
So I don't manage to speak. Yes, okay, good. Yeah, so that was the idea, right? So what I had in mind was to talk about these excitons as illustrated here, right? That can be created in 2D semiconductor materials, as shown here in this cartoon, right? So there are two types, like one that is coupling strongly to light in a single layer, but then you can also have these objects here, and they are quite sort of exciting, interesting when you come from the atomic or AMO side, right? Because they have a lot of properties that we just have heard about the whole morning, basically, in the context of molecules, right? So they have a strong dipole because the electron and the hole here are separated by like 1 or 2 nanometers. So there's a really strong and large dipole compared to the typical distances. So people can twist these materials, create lattices, just like, or similar, let's see, at least in theory, how we do with optical lattices. And they have amazingly long lifetimes of nanoseconds, essentially, right? So all the things that we like to do in AMO, they can actually be transferred here. And I think this is really, at least from our side, so the part that is really quite interesting. So we are not, as we often do with like many of these atomic architectures, sort of simulating solid state systems, but we can actually take some of the ideas that we've been working on and see how they apply to the solid state. So they often don't do exactly, so you have to really worry about a lot of other things, so they are not as clean as atoms, and if you do this seriously, you have to think about phonons, disorder, and all these kind of things in a meaningful way. And this is what I wanted to talk about. So essentially, sort of focusing on these three sort of main topics or buzzwords, as you say, like coming from the optics. So looking at cooperative decay, so superradiance and strongly interacting systems, and trying to see how strong dipole interactions can affect these things, which is a feature that we, at least right now, don't really have in atomic systems. So these state-dependent strong interactions, at least for these sub-wavelength settings. Then also talking about artificial photonic interactions, so polariton interactions. We've already heard about that in a different context. So here using actually something like molecules or bound states of two excitons that form due to dipolar interactions in such lattices. And then finally, also very recent experiments that are right now, I think, still in the regime of collective decay, but where you actually really can see these coherent collective effects. So in like different or non-exponential decay dynamics here as a function of the density of these excitons. So these are experiments going on at Emory. And again, so I was trying to, or like actually planning to cover these things. But in fact, looking at all the great talks, so there has been a fantastic talk by Anna yesterday, and Susanna actually covered all these things. And what I understood from Hussein is, in fact, that maybe ideally we would like to sort of cover more of a range of AMO theories. So I kind of thought, okay, also seeing the abstracts of other talks this morning, that I would stick sort of in the world of dipoles, but then actually trying to pick up on what basically Thijs actually finished about in his talk. So basically, I would like to tell you a little bit, or some thoughts and some recent work that we did, sort of trying to address the question whether, like now following up on these amazing experiments. So you just showed in the end, so the experiments from Sebastian Will, right, at Columbia. Now that we have these molecular BECs where the dipole interactions are stronger, so is it actually interesting? So can we see like more or new physics, or are there challenges compared to what we have witnessed sort of the last couple of years or 2 decades, in fact, on magnetic atoms, right? So is going stronger actually more interesting or better? So that's kind of what I will try to at least touch upon from our perspective in this talk. So in a nutshell, it means actually like we are playing with dipoles, and if you do this classically, so this is typically what happens. And that was also the expectation what people thought actually would happen quantum mechanically, right? But as we know now after quite some years, so things are more interesting, and so that's kind of the topic of the talk. And this actually goes back like quite some years, right? So I think that's one of the first like pioneering like works in Tillman Faust group that started this whole field of dipolar BECs with chromium, which are kind of having like weak dipole moments for our standards now. So I think this is the first, right, where they demonstrated like a BEC, and essentially what people then realized after some time, so using our typical description of BECs, and that will also be important here, so trying to see how we can actually understand or improve on this, like substantially now having these strong dipoles of molecules. But if you apply now a complete classical description, so the equivalent, so the classical field equivalent of this movie here, right? So we also see collapse basically. So there's really nothing sort of additionally new coming in by treating the dipoles as a wave function. So if you have this classical field description, right? And again, this was also seen in one of these early experiments from Stuttgart. So where you see here basically like a collapse of the BEC, right? Due to this attraction of dipoles, just as you see here, and this really nicely, you could say nicely is reproduced by the Gauss-Biediewski equation. But on the other hand, it also tells you there's not much quantum going on beyond like simple mean field effects. And so that this has changed. Then a couple of years later, so that's another paper from Stuttgart from 2016. So where they're now really like against all expectations from the theory at the time, so that there wasn't any collapse, right? So there were these structured states forming, right? So as we know now, like these quantum or droplet states basically that stabilize themselves, right? And in fact, you can understand that, and I also will come back in a few minutes to that, so you can understand that similar to the physics of helium, right? And so if you look at again some kind of field description, right? You can calculate the excitation spectra of these BECs, right? And due to the long-range interactions, so the fact that it's not just a momentum-independent contact interaction, there is some structure here, right? And they can have these minima, and if this minima goes low enough, these Roton minima, then you basically have an instability, right? It's also similar to what you see in optics, right, where it's called modulation instability. And so since then, this really has taken off. So I just want to give like some perspective. So talking about the future, I think you also have to look back, right? And I think it's really like just starting from this one experiment here, that a lot really has happened, right? And now it's 10 years ago. So people in the end sort of actually found these coherent versions of these states, right, which we now call like some analog of a super solid. There were lots of studies of these droplet structures, excitations, and understanding really has improved a lot. And so I think what I find really exciting here, that there's really like experiment is feeding a lot to theory experiments, theory developments. So it's not like often that you make predictions and experiments are then trying to reproduce that, but there were actually quite a few surprises, because even though like it's kind of an old problem, like a weakly interacting BEC, so there are actually a lot of unknowns, or if you say deficiencies of the theory, that are really magnified by these dipole interactions compared to sort of weakly interacting local interactions in BECs, right? And so basically, so that's kind of the slide that I'm trying to sort of go along, right? So you see here the strength of the dipole interactions, or the length, the dipolar length, and the okay, so here we are, and the strength, right? So here we have our typical alkaline atoms, and then as I just said, so I think the last 20 years, so really having this jump by 2 orders of magnitudes has really led to a lot of interesting physics. And I think the question where we are now, that these BECs have just been made this year, so can we expect like similar sort of interesting physics to come out? So we're not gonna sort of make a prediction, but I think so there are really sort of reasons to think that we can actually learn still quite a lot by going up in the strength of the dipole moment. So here, as you see again, by orders of magnitudes, and that's kind of some of the points I will try to make. So is actually going to stronger dipoles, so is that really giving us new challenges or new questions to address? And so again, like to address that, so let me just go a little bit back and talk about like sort of main findings of these atomic dipoles, where you can actually already see some sort of problems that were in the theory, right? And the main motivation for most of these experiments was actually sort of the sort of goal to sort of realize in experiments these what's called a super solid, right? So a solid superfluid. So this goes back like many decades to Leggett and others, and how you can, or how we would like to picture this, and how it hasn't been really realized in atomic systems is sort of shown here, right? So you could think of a solid and put it in some rotating container, and then the whole thing would sort of move with the wall, right? And if you have some sort of superfluid fraction, the idea is that it would be decoupled, right, from any sort of forces. So there should be some coherent superposition now, but not of a fluid, but really of a rigid solid and some fluid component. Right? And that, as most of you know, of course, has been believed for a long time to sort of be to exist in helium, but even like until now, so there has been no clear evidence. And what we know now or have seen in experiments with magnetic atoms is actually not the type, I think this is one should really point out, right? It's not the type of sort of supersolids that people have been thinking about like 50 years ago, but it's really more in the sense of a fluid picture, right? So mathematically it's actually equivalent, but sort of physically it's really more something that Gauss himself has sort of described like even longer ago, where you have a spatial modulation, so a spatial symmetry breaking on top of a superfluid fraction. And I think so one of the perspectives for these molecular systems is now that we actually have the interaction strength to sort of probe this physics and see whether these kind of things actually really exist in an actual physical system, because we have full control over interactions and parameters as opposed, for example, to helium. Right? And that's what I would like to sort of touch upon in the end. But let me just briefly now go into a little bit of the theory sort of behind these sort of more fluid-like dipolar supersolids, right? So again, as most of you know, so the really key sort of ingredient or addition is actually to go now just slightly beyond mean field theory here, so this Hamiltonian that I've shown before, right? And add sort of now a back action, so some effects of quantum fluctuations, right? So fluctuations, again, are just these excitations that I have shown before, right? So that's the excitation energy, so the spectrum as a function of the momentum. You can see these photon instabilities, the corresponding sort of quasi-particle amplitudes for these excitations, for group of excitations, you call U and V, and then I can simply calculate the energy here as the interaction of these excitations with the BC, right? So it's basically just some interactions of these sort of non-condensed atoms sort of flying around the BC. This can be easily calculated from here, and what you get out is sort of also known for a long time, you see, like since the 50s as the LHY correction, right, to the equation of state of a Bose-Einstein condensate, and this is all nice and well confirmed for local interactions, and often in talks it's also described as sort of a standard thing for dipolar interactions, but there's actually a problem. Yes? Yeah.
So I know that if you just calculate the energy, you get this correction.
Mm-hmm.
But is it really local in position, like you've written in this Hamiltonian?
That's one of the other approximations.
Okay,
But
so
I would argue this is actually not the worst part about
Yeah, sure.
about the theory. Right? Yes, otherwise it's super hard to do. But that's, it's kind of not too unreasonable to do that. But then if you the bigger problem is that when you evaluate this integral and you work, or you want to look at parameters sort of where this minimum here becomes really, really low, then you get to the regime where these excitations are actually unstable, right? And yet we use them to calculate an energy. So what we typically do is to actually use this expression here, right, which is kind of where you can evaluate this analytically. But strictly, it's only valid when this dipolar interaction strength, so this was described also in Ty's talk, right? So that's the ratio of the dipolar length to the local scattering length, so when this is very, very small. But that's actually the regime where nothing much is happening, right? So where the VC looks like short-range interacting system. So the interesting physics actually happens when epsilon is around 1, right? So when these things become unstable. But yet, mostly we actually use this expression here, and it still does a qualitatively good job. Right? But if we would evaluate this integral here fully, so exactly because of this problem that I just said, right? So the excitations become unstable, we actually also get an imaginary part, right? Which is inherently unphysical, basically. So it means we shouldn't use these excitations to describe this kind of physics, but typically this is very small, at least for the parameters of the atomic BC. So what we usually do is we just throw it away and say it's just a few percent, and then we hope for the best. And of course we have been doing this because it's a good strategy. So if you do that and like you use this theory that's not completely sort of well-founded, right? So we can still even quantitatively fairly well explain sort of at least the stability of these droplets and the properties of these supersolid states. So here's a comparison, for example, from Innsbruck experiments, right, between sort of measured densities here in the experiment and the calculations, right? So it's not perfectly the same, but the predictions are actually not so bad. On this, at the same time, now over the years, it's also clear that there are actually quantitative discrepancies, right? And but it's completely, like it's not really clear whether they come from these problems, right? Or whether they come from these local density approximations or actually other effects in the experiments. And the main problem is that they are also typically very small, right? And that's going to be different for the molecular systems. And there are other sort of theories, for example, based on sort of weak three-body interactions and sort of variational principles of squeezed Gaussian states that are also describing experiments fairly well. So there is still, even after those years, I think that's an important point to make. So there are still quite some discussions going on, even though this is a fairly sort of old problem, just talking about BCs, right? But adding these dipolar interactions makes things differently. And so what we then did recently, and this I just want to throw in this context, is actually try to, like if you want to try to find more evidence or sort of test sort of this idea of sort of just only describing interactions with fluctuations, you can look at other fluctuations, right? Like thermal fluctuations, basically. So they can just be added by the same theory, and that's what I briefly want to go through, right? So now we go away from the ground state, we add sort of a small but finite temperature. So now you have to do a little bit of thermodynamics. You look at the free energy, but again, I can calculate is pretty much the same within Bogoliubov theory. You get very similar expressions than for the corrections to the ground state energy from quantum fluctuations, where the temperature now is coming in, and essentially you just get this weighted sum now over the interactions with the thermally excited excitation. So it's all very standard, right? And you can transfer this to dipolar systems. You get these kind of expressions, right? And in the end, you obtain like a very, like just another sort of correction to your Gauss-Berdievsky equation, right? And that you can do and kind of try to test the theory. So that's what we did. And then to some surprise, at least at the time, so what you find is actually that increasing the temperature here now is now lowering your excitations, right? It's not sort of the pressure that normally, like the quantum pressure that we had shown before or seen before, is sort of raising energy, is stabilizing the BC. So it seems like temperature actually has a different effect. Yes.
So are you still, I mean, so temperature in principle is in two places here. One, it's in the corrections you just derived, and then you should also treat the Gross-Berdievsky at finite temperature, or are you just solving Gross-Berdievsky with this?
So this is what this is doing, basically. So you are talking about
so
Wigner
only thermal
type.
effects are just by adding this extra term.
Yes, but it's equivalent. It's actually, so this is more than sort of the average. That's from the equation of state. So it actually gives the same. So there people have been doing this now. Like you're talking about this like Wigner type calculations, so where you add noise, or
No.
what are you referring to?
Well, so I mean, in principle, you've integrated out these thermal fluctuations, right? And that's how you get this extra term. But I guess that
so it treats the interactions basically of the excitations with the BC, and it's
yeah, I guess
it's a good thing to do when they are weak.
Temperature approximation, I guess. When you
Which we do basically exactly. Yeah. So this is like this should be having a small effect on the BEC function, right? There's a macroscopic BEC. Yes, yes.
But you cannot do dynamics with this equation. This is the point. So you cannot really do dynamics.
I cannot do fast dynamics, right? But I can do slow dynamics.
Why?
If it's adiabatic, I can do it. No?
I think it
Yep.
also has to be like near equilibrium dynamics.
Exactly. Yeah. Yes. So you can let it. I mean, you can. Yes. It's also not what we do, right? So you can look at
This equation was
at equilibrium, basically, right? But I can look at like imaginary time dynamics, for example, and I get the like the finite temperature equilibrium. But you're right. Yeah, you cannot do like you cannot quench the system and see where it's going. Yes. Yes. It's also not what I'm writing.
Exactly.
Yes,
I
yeah.
saw
Yes,
it.
yeah.
I wanted
Yes,
to know
yes,
that
yes,
you
yes.
cannot do dynamics with
Yes, fine, yes. Yes, but then we actually find out so that, as usual, you should read also like historic papers and you should read them well to the last page, right? So that's this picture I showed in the beginning and that everyone knows actually in this context, right? And like again, I said, like we got very excited about this temperature dependence. I also was a bit worried whether it's correct, but then like if you take the same paper here from the early 70s and you really read it to the end, so people have actually already looked at this in helium, right? Like at the sort of dependence of the spectra for finite temperature, and they see very similar effects actually, right? So that sort of the energy, so the gap of this photon actually also in helium, which again is nice, right? So we have a nice sort of correspondence here to, if you wish to simulate the physics, but they also find, as I said, so that the energy goes down, right, of the photon minimum. But importantly here, so what like in all, for all cases basically, all like densities or pressures and temperatures, so they basically this photon minimum always stays finite before or until you hit sort of the transition to a normal fluid, right? So they never really find the case, and you will just see that this is different for the BECs, where sort of this photon minimum goes to zero driven by temperature, and you still have a superfluid, right? So this just generically doesn't happen. Mostly it's due to the fact that here it's actually a weak effect, right? Because it's coming from interactions purely between excitations, so there is no large BEC fraction in helium, so the physics is actually quite different, right? And sort of in our case, and this simply really doesn't play a big role for the helium physics, so our interactions are in a sense like one order higher, right? So it's the interaction of excitations with the BEC, not interactions between excitations. And because of that, you can easily get to the regime where temperature is driving now these photon instabilities and is actually driving this sort of formation of structure, which is thermodynamically kind of unusual, right? Kind of surprising. So you could say there is a temperature-driven phase transition that takes you from a fluid to a solid, right? Which at first glance is kind of against what you would expect, like at least in a strongly correlated system. I think I have to speed up a little bit, right, if they want to get to the molecular point. So let me just say, so there has been, like before, again, like all of this was motivated by experiments, so very nice experiments in Francesca's group, where they indirectly, or they actually found evidence that's kind of hidden here in this plot for that. So let me just briefly sort of walk you through this. So what they do there is actually dynamics, right? So they take a BEC, they evaporatively cool the BEC, and mainly they wanted to ask the question whether sort of the formation of the supersolid either goes through the classical phase, so like really a classical crystal, and then the formation of coherence, or the other way around, if you first have a superfluid and then grow these instabilities. But on the way in this experiment, they actually found here this sort of surprising effect of the temperature, right? And it's a little difficult to see, so basically there's a lot of different quantities now here shown as a function of the evaporation time here, right? So this red line shows the number of atoms in the condensate, right? So it goes up as you condense, and eventually it goes down as too many atoms evaporate. So there are two times where you have the same number of atoms in your condensate, okay? Then the value of these points here shows you the modulation. So if it's zero, it's a flat state. If it's modulated, you have these sort of supersolid-like structures, and then the color of the, like on these dots, right? So that's shown here, that's the temperature. So there are three different things all in the same plot to kind of grasp what's going on. I think here it's enough to just look at these 2 points, right? So they are at the same density. Earlier there is a higher temperature, where they get this kind of state with a high modulation, and then at later times when temperature is low, there's a flat state. Right? So it's exactly kind of what I just described, yes?
Yeah, so I'm curious if I understand, but I'm not sure if I understand things, but it looks like from the picture on the left that there is like a order in the evaporative cooling. So
yeah, that's just a cartoon, but okay. Yeah,
is
yes.
the curve going to be the same whether you lower the temperature and then subsequently raise the temperature? Or would that be an
It should be. It should be, right?
Right. So there is
yeah,
no
because it's a finite system. Like a large system, if it's the first order transition, there is some hysteresis, but yes.
Okay.
So it's like a crystallization transition, but yes. And yes, so there is hysteresis in 2D. What they have here, it's a first order transition. And here, just to show that actually, the description now, so this was my main point of the experiment, is actually not so bad. So what we did here, so is we take the value of the temperature and the value of the density, like along this time, right? And then we just color basically. We take this continuous color away, and we just color the plots, the dots here, the experimental dots, just blue when there's a flat state, and yellow when there is a modulated state, right? And kind of quite remarkably, actually, like this fairly simple theory that, as I just also said, has quite some flaws. Again, describes the physics here quite nicely. Right? And so now I spent a lot of time talking about atoms. So what I wanted to talk about is actually the molecules. But I think it's just another example again, so where we found something that was not inherently really expected in the theory, and it's really the experiment sort of driving these sort of improvements of the theoretical description. Right? And I really think, again, so that this will now happening now with going to the stronger dipole-dipole interactions that we have available in molecules. And I just want to give a few examples. So that's a slide you've already seen in Theis talks, and now we have these PDCs, right? They have stronger interactions. There is potentially also higher densities in these droplets. And there's another actually quite important and interesting feature that is coming from these very nice microwave dressing schemes, that we can also tune the interactions in very different ways, right? So, for example, if you just take sort of the simplest sort of single field microwave dressing. Now, first of all, from the shielding, right, we have this core, so you get more of a sort of molecular type potential, right, with a minimum where we have some long-range bound states. But then, and Theis already mentioned this, right, if you look in detail now, so this is also reversing the sign of the dipole-dipole interaction. So there's a different dynamics now, or a different type of system where dipoles that are like this are attractive in two directions, right, and if I put them like this, they are repulsive. So we are kind of reversing the geometry, and as you will just see in a second, so what that means is that structures that were 1D before, they are now becoming 2D, and that also makes, of course, things more interesting. So here maybe just one like slide, like about like orders of magnitude. So these are different potential plots now that we just made from, again, like from this simple scheme here, right? So where you can tune these interaction strengths simply by the tuning of the microwave from the rotational resonance. And for far detuned states, we can sort of at least artificially generate sort of conditions that are similar to the atomic case, to dysprosium, right? And if we go close to resonance, we have sort of these strong dipole-dipole interactions. I think this here is for calcium fluoride example, right? And just to put this into context, what I'm doing here is I take the minimum of the potential as a scale, right? And plot these different potentials here, and you see like what we would have for dysprosium looks like this, right? And these are now these stronger interactions, and it's actually not far away from what you would have like for the scaled potential of helium, right? So we really now also get, I think it's also good to have this sort of perspective, this context. So these atomic or these molecular systems now get to the point where we can look into the sort of more traditional low temperature physics of helium with the additional sort of feature that we can tune these interactions, right? We can tune the interactions, you can play with confinement and so on and so forth. But given sort of all these problems with the simple theory that I've just shown, we also expect these mean field theories maybe to be less applicable, even though the interactions are still weak, right? We also have to keep this in mind, that for most cases when we start to look at the transitions, there are still weak interactions. But just to probe basically like this kind of physics, so what we did now as a first step was to do now some exact calculations, and I'll show you in a minute that one has to be very careful here, right? So we do some path integral Monte Carlo simulations, which are now very similar to this classical example here, right? So we just simulate like a few hundred or less than 100 molecules. Right?
Are you actually doing PIMC or like warm or something? Isn't it tough to get?
It's warm algorithm, yes,
Oh,
yes,
okay.
yes, but it's a path integral. Yes, so here's one sort of example. There has also been a recent work from the Barcelona group, from Jordi Bornat, where they look at these problems in free space. So what we had focused on here was to simplify the situation and first look at a sort of quasi one-dimensional system where you confine now the dipoles in this geometry. So there's a long tube, just like I've shown for these finite temperature calculations for the atomic case. And the first question we asked, so is there some, like what happens to this gas, right? So you start your simulations from some finite density, you will let it run, right? And then if the interactions are weak, right? So this C is now a single parameter describing the interactions, so we see that it just spreads, right? So this is what you would call like a gas phase, but then if you make the interaction strong enough, very similar to the sort of atomic case, then the system doesn't collapse, right? Even though there's an attraction, so it's quantum mechanically. But it converges like to a finite size, right? So there is still this physics, again, of these quantum droplets, even though the interactions are a little bit different and stronger. And sort of you can basically map out, if you wish now, some kind of phase diagram. I just show this in a minute, as a function of this trap, of this confinement length here, right, and the strength of the interactions. If you now play with the interaction, we also see, and that was actually quite exciting to see, right? So we also see now similar physics that we have seen for these weak dipoles, that at some point, if you confine the system strong enough, there is some structure appearing again, right? So it looks like these droplets should also be sort of happening, and these are basically for real out of experimental parameters. These droplets are forming. Okay, yep.
So when you do the simulation, when the things contract, does it heat up or you pull it down?
Oh, you should be careful how you interpret this. So this is not dynamics, it's not time. So these are really like Monte Carlo updates, basically, right? You start from some initial configuration, which is a classical state, typically like points. And then you basically do, so this is not a physical time evolution, right? So these are just Monte Carlo steps.
There is no conservation of energy
Yeah, at finite temperature. And it's not real-time dynamics. It's like it's a dynamics in the beta in temperature. Basically, it's like an imaginary time, imaginary time evolution. So you really shouldn't, I think it makes sense to look at this point and at the final point, like how this evolves here. I think one shouldn't really give it any meaning. But it shows there's an unconfined state, right? And there are confined states. I think and these things can be trusted, right? So once this is converging, we can do averages and get basically observable. So here you couldn't even do it, right? Because the state is still changing. But it's not time.
Thomas, how do you scale the distance from the previous plot? Here? So
Yes, I just put it here. So this L is essentially close to the minimum of the potential.
Is that the core of the interaction?
Yeah, it's kind of where the potential hits zero, essentially. So it's close, like 1.2 something is the minimum, right? So when the density is 1, you're basically sitting in the minimum.
But can you sort of build a sort of a standard classical model where you basically start to squeeze all the particles within until they basically their force touch? Or is it more complicated than that? Because I think that's the sort of difference with respect to the dipolar droplets, where the system is still sort of dilute. Here it looks like that.
If the density gets to the point where you hit this, yes, so when the density gets close to 1, yes, so then this whole contact interaction idea breaks down, of course. But if that's what you are talking about.
But that's also different, for example, from what we've done in the past for the...
Yes. So you really have to take here the real potential, right? You cannot take an effective interaction anymore.
Yes. Sort of trying to understand whether, for example, this plot here...
Here it doesn't happen. So this is in the weak interaction limit, basically, still. That's also important, right? So in principle...
Right, but when you rescale this x by that length that corresponds roughly to the core of the interaction, when you see when you compute the distance between these dashed lines, basically the particles, the average distance between the particles is twice the core of the interaction, or not?
Okay, so this is an integrated density, right? You have to look at the density. here, right? So it's not so easy
Maybe
to
when we can
say. So
discuss
the
it.
distance is larger. They are actually.
It is larger than twice the Pohl of.
Yeah. Like,
Okay.
yes. But that's the interesting regime where you want to go,
I
and
agree,
I just,
I agree.
I'm not sure I'm getting there. So,
Okay.
but yes.
I'm gonna ask you a question anyway.
Mhm.
So, if you start.
Okay, I thought you were pushing me to finish the talk.
Oh,
Okay.
no.
That's it. Okay. Yeah.
You have 10 minutes, I think, so, accounting questions, but if you start from different initial classical configurations, do you always end up in the same?
No, that's one of the important points I wanted to make. Where, like this ab initio, like with generically, this is a good method to really calculate these things. So here, it actually turned like, and this really made a biggest problem in actually calculating this phase diagram. It's not like this. Right? And it's like one of the few cases actually that I know that really makes problem. But here we think so we are kind of like that. This is kind of converged. So it takes a lot of trying, like different configurations. You look at the energy and things like this. So you can't just let it run. I think that's an important point, right? But we see this kind of phase diagram, right? And maybe it's kind of what you expect. You increase interactions, and then we get these sort of arrays of droplets forming, right? And what's important is they are more like the geometry of these droplets is more like coins, right? So you get arrays of these really flat systems now, and the stronger you make the interactions, the more flat they also become, which I think is interesting. So they really spontaneously, if you wish, they become 2D, so they get confined in 2D just from these anisotropic interactions. And what we wanted to see is basically how this is going on, right? And how we can go to this, like to the thermodynamic limit, and if we can speak of a super solid state at some point, right? But there we are not. So we are not yet quite there, but precisely because of the problem that you mentioned, right? So this is one of the earlier simulations where we got quite excited, right? So what we do here is to start in a regime like this, right? And then just increase the particle number, which becomes hard at some point. But if you run this long enough, and then we actually see that more or less linearly in the particle number, we see the number of droplets growing, which is exactly what you would have liked to see and expect, right? So there is a solid basically coming out, and you are approaching the thermodynamic limit. And so that would have been like a super nice result, right? But then if you look at it more carefully, then we see exactly the effect that you mentioned, right? So like these examples are, I think for this one here, you see here now so I shouldn't say time resolved simulation, so it's not time, it's like the number of Monte Carlo steps, right? So where we start from a density like that, right? So that's just the ground state of the trap, non-interacting ground state. Then we let it run, right? And once in a while you can make these sort of averaged snapshots after letting the system evolve for some time, right? And you see these nice sort of two separated droplets forming. However, then if you do exactly the same thing, like same parameters, but just starting from a different initial density, they actually converge to a single droplet, right? And then you compare energies, and this energy is actually lower than the other one, right? So it really shows that the Monte Carlo is not working as it should, right? Like in theory, it is actually exploring, or it should be exploring ergodically all of the phase space, right? And give you the equilibrium state, but it really badly fails, right? Like if you try more, you get all sorts of numbers of, or if you go to lower densities, you can also get more and more droplets. And there's a simple explanation for that, which is really sort of specific to these sort of cluster crystals, which are kind of characteristic for these kind of BEC systems. And now we are looking at these cluster states in a strongly interacting regime, which is different from the atomic cases, and bringing both together really is challenging the numerics, right? So what we would, in a dynamical picture, expect to see, right? If you have two droplets that are far away, they have a strong interaction because there are many atoms, they should actually attract, right? But then if you think about what you do in the Monte Carlo step, it's not a real-time dynamic, so we don't let the system sort of evolve like according to the interactions, to the forces, right? But we do local updates typically, right? And you have to do this inherently in the setup to also keep track of the symmetrization and so on, right? So we do a local update, and we ask, how is the energy changing? Is it favorable or not? If it's unfavorable, we actually put it back, right? And what happens now, if you really have these dense, strongly interacting droplets, it unfortunately turns out that the energy loss that you have from moving just one atom or one molecule away from the cluster is, in most cases, just significantly higher than the energy gain that I'm getting when I'm moving here, right? So if I could move the whole thing, it's different. So then the relative energy doesn't change. But that's not how these methods are built, right? So we believe that this is really the sort of the problem in the algorithm. So the steps are always rejected. And you can actually test that. So that's just the first initial sort of step. You can now try to improve the algorithm. So allow the system to do now collective updates, which is something that you normally wouldn't do. It has a lot of problems. Again, you also have to take care of symmetrization and so on. But it's just to see whether this idea is true, right? So now we also allow, like if you start from a state that really has two separated toplets, you can group them, right? You can clearly assign sort of a group to one cluster and another group to another cluster, and then allow in the Monte Carlo simulations collective steps where we move all of them, check for the energy. And there we indeed see that if you do that, like an initial configuration that would be completely frozen in the standard Monte Carlo simulations is essentially approaching each other in these states, and then at some point they get stuck again because of the interaction. So this really shows now there's also some work to do on the numerical side, right? So all the methods that we have, they really don't work, and if you want to have reliable predictions for these molecular systems, we really have to get a better idea or to improve our numerical methods. Right? So what I wanted to talk about, and I just have 5 minutes. Right?
Well, including questions, you have 4 minutes.
Okay. Including questions. Okay, so then just very briefly, so it's just something like I would be like happy to discuss also later on. I just touched upon this in the beginning. So now these molecular systems, they also so really enhance sort of these conceptual flaws that we have when just doing a basic sort of description of a weakly interacting Bose gas, right? Which is a very old problem, like many decades back, but there are flaws that are still there in the theory and that haven't really been resolved, right? So for example, the standard procedure that everyone has been using also back in the early days of BC physics, right, is Pohl theory or Hartley-Fock-Pohl, if you want to describe the back action, right? It's just solving the set of equations. That's something we have been doing and other people have been doing for these dipolar systems, also for contact interactions. But what is known there is that if you do that, right, if you add this back action, you introduce a gap in the excitation spectrum. So the physics doesn't really work out anymore, right? And that's typically then solved using the so-called Popov approximation, where you throw away all the terms that generate the gap. But then in our case, it actually makes a problem, because if I throw away terms, I'm getting wrong numbers for this energy correction, right? So for contact interactions, it's not a big problem because this back action doesn't play a role. For molecules or for dipoles, it actually plays a role, right? So each of these sort of established methods, they just don't work, right? So we could use them for the weak dipoles, right? But now going to this even like stronger or more highly dipolar systems, we just can't use them anymore, right? And it's not a big surprise that the methods really don't work. And so that's something we've been trying to improve upon. And what we stumbled over is like these papers from the early 2000s from like Sam Morgan, Keith Burnett, and many other names that you all know, where they actually proposed to sort of upgrade, if you wish, like a description of the interaction between particles, right? So typically we just use the T matrix here in the low energy limit to derive a scattering length. So just solving this Dyson equation, right? And so you can go and try to include approximately many-body effects, right? So the simplest one would just be you go like self-consistently to next order. You get these density terms here that come from the fact that you have bosons, right? So I can change the kinetic energies of free particles and replace them by the excitation spectrum, right? And if you do it, then the whole thing becomes very complicated, which is one of the reasons why many people really haven't looked into it. Another reason is that that's what we did now recently, if you apply the theory, at least in the simple limit where you can deal with it to a homogeneous gas, and you look at like standard problems, right, for contact interactions, you almost see no difference, right? So it actually really doesn't matter. So the theory may not be fully correct, but it doesn't really make much of a difference. If you do the same, even for weak dipoles, like to our surprise, you really find sort of really big differences when you get close to this instability threshold, right? So the dashed lines here show the like old theory, so to say, using Pohl theory slightly beyond this sort of instability threshold, and if we do this many-body T-matrix calculation, so we actually find that the gas is still stable. So I think so there's a lot of still interesting physics, I think, sort of hidden in this system that we just didn't really pull out so far, and I think mostly because experiments haven't been in the regime where they are becoming important, but now they are becoming important, and I think so these are one of the two sort of interesting perspectives, I believe, right? So when you go to these stronger dipoles. And like the final one I just mentioned already, and I just want to sort of touch upon briefly, right? Like now looking at these interactions again that we have seen in Theis' talk, right? These sort of anisotropic interaction. If you just look at the energies, right, that you see then when you expect what Tommaso already mentioned, right? If you go now to really strong interactions, you can actually see that just also from classical arguments, right, is that this anisotropy of the interaction will actually really have an effect on the geometry of the system, right? So for these atomic dipoles, you would have expected to see like 1D structures. They are not stable because in the end it's 1D, or you don't see crystalline states, right? But if I flip the dipoles, which I can do here with the molecules, there's actually now a chance that sort of without any confinement that the system could actually self-assemble again, and maybe this is sort of a link to what I actually wanted to talk about, right? And to a 2D sort of quantum material, if you wish, right? And what I think would be really exciting is, since we can now tune these interactions, we can like really change the strength and maybe just go to the edge where crystallization happens. There might actually be a chance that we actually see the real super solidity in these systems that people like Leggett and so on have been thinking about 50 years ago. So I think that's would be really like a big thing coming out if that's possible, right? And that's kind of what we are trying to do right now. The problem is, as I said, so there are really no good methods that can deal with these things at the moment. Now I'm done, but I'm unfortunately pretty much used up my time. So here are all the people that contributed to like both of these parts. So most recently now we are discussing with Tim, who also moved to Vienna just about a year ago, right? And the idea, he has been feeding us a lot like with these ideas on the molecular physics. So that's the group right now in Vienna, and it's actually Casper and Jan and Matteo who have been like, doing all the work I've been talking about. Thanks.
Thanks, Thomas. Maybe in the interest of time, why don't, Tommaso, you come get set up and we can take a question while we make the exchange.